Hey everyone, let's do section 3.4, partial fractions. So this is just another technique of integration. Let's think about how you combine fractions into one fraction. You have to have a common denominator. So partial fractions is just going to do exactly that, but backwards. So we're going to split up a fraction. So for this first example that you see here, 1 over x minus 2 plus 2 over x plus 4, the way you would combine those two fractions is you would multiply the first fraction top and bottom by x plus 4. You would multiply the second fraction top and bottom by x minus 2. You would then distribute this 2 of the second fraction, combine your like terms on the top. That's how I ended up with 3x on the numerator. And then they would have this common denominator, which if you were to FOIL out x plus 4 times x minus 2, you would get x squared minus 2x plus 4x minus 8, which is the common denominator of x squared plus 2x minus 8. So the real question now in terms of integration is to work backwards. So how is it I could figure out if I wanted to work backwards, which fraction would have the 1, which fraction would have the 2? That's what we're going to be dealing with today. So let's do this example. We're going to use partial fractions to find what's called the partial fraction decomposition of this rational expression. So what you're going to do is you're going to first take your expression, which in this case is 3x over x squared plus 2x minus 8. You're always going to start off by factoring the denominator completely, whatever that takes. So make sure the denominator is always as completely factored as possible. So in this case, that's x plus 4 times x minus 2. And then you're going to hope to set that up into a couple of different fractions. That's the deep partial fraction decomposition. Now, how do I know there's going to be 2 fractions? Maybe there's going to be 3. Well, I know there's going to be 2 fractions because the denominator has 2 factors. So the first fraction will have one of those factors, the second fraction will have the other, and then what I don't know is what's on top. So those are sort of like my question marks. And rather than calling them question marks, they're unknowns, so we should just give them variables. We've already used the letter X here, so I'm going to use the letters A and B. You could choose Y and Z or Q and happy face. The variable choice doesn't matter. And so then the question is to solve for those unknowns. And my unknowns are A and B. So the way you solve for the unknowns when you have now a rational equation is you are going to multiply both sides of that equal sign by the common denominator. So I'm going to multiply the left side by x plus 4 times x minus 2, and I'm going to multiply the right side by x plus 4 and x minus 2. And then I'm going to see what happens. So on the left side, when I multiply that, you'll see the x plus 4 cancels and the x minus 2 cancels, and I end up with just 3x. On the right-hand side, when I distribute this entire x plus 4 and x minus 2 across that equal sign, you'll be able to see that sometimes one of the things is going to cancel and the other one wouldn't. So for that first fraction, you have an A, the x plus 4 canceled, but the x minus 2 did not. And then for that second fraction, the x minus 2 canceled and the x plus 4 did not. So that was called clearing the fractions. That's a common way to say it, is that we've cleared the fraction, or just what I say is I multiply both sides of the equal sign by the common denominator. That's always step 1, is to multiply both sides by the common denominator. Then we're going to try to find A and B. So I'm going to show you, and this is going to be really important, so make sure you're clear on your notes. I'm going to show you 2 different ways. So I'm going to split this screen up into 2 different ways, 2 methods. There's not really one that's better than the other. Sometimes I like one versus the other. Once in a while, one of them will be faster than the other, but really there's just 2 methods that are going to get you to the same place. You'll decide which one you like better. Okay, so I'll walk through all of the steps. So the first method is I'm going to go ahead and distribute, and that would give me 3x equals ax minus 2a plus bx plus 4b. And then I would combine my like terms. So ax plus bx minus 2a plus 4b. And to combine my like terms, really it's a plus b times x, and then minus 2a plus 4b. So what I did here is I just took the things that are attached to the x and I put them right next to each other, and then I did the things that don't have any x at all left alone. So kind of combining the like terms. Then, and this is the important part of this method, kind of the name of this method, is to compare the coefficients. So now you are going to compare the coefficients, and I'm going to write these in a different color to help you visualize this. On the left, the coefficient of x is 3. On the right, the coefficient of x is a plus b. So I need to equate those coefficients. They have to be equal in order for this equal sign to be true. And then the other thing is the other coefficient that I have is the thing that's in front of no x at all, or what we call the constant. On the right-hand side, there is no constant, so the constant is 0. On the left-hand side, my constant is negative 2a plus 4b. And now you have a system of equations. This is now a system of equations where you solve for one variable and then plug it into the other, just like you solved any system of equations before. So for the first one, I would have, it looks like a is equal to 3 minus b. And I'm going to draw this little arrow. Now I'm going to go to that second equation and replace what I have. So 0 is equal to negative 2 times 3 minus b plus 4b. And then I'll simplify. Okay, this is the part that might feel a little tedious if it's been a while since you've done some of this algebra, but this is purely algebra. So just kind of standard basic algebra, combining like terms, trying to solve for your variable and all that work, and I got b equals 1. And then I would take that and go into the other equation to solve for the other letter. So a is equal to 3 minus b, which means a is equal to 3 minus 1. So a is 2. And then you have everything that you need. We figured out what a and b are. So I can take that a and b, the solutions I got, and go back into that partial fraction decomposition. And so now I have, if I were to rewrite that, 3x over x plus 4 times x minus 2 is equal to a over x plus 4 plus b over x minus 2. And I just replaced my a and b with what I found. That is the partial fraction decomposition. Cool. Okay, and then as promised, I told you there is another way. And like I said, this way that I just showed you is sort of the guarantee. It's going to work no matter how complicated these get. This other way I'm going to show you, sometimes it doesn't really work very smoothly, but sometimes it does. So it's worth having an extra tool in our tool belt. So it's just going to be another way to solve for a and b. I already know the answers. My a was 2 and my b was 1. But let me show you another way I could have gotten that without having to do quite as much algebra. So let me go back to where we split it up. Remember, we factored and we set it up as 2 different fractions with a and b as my unknowns. And then we cleared the fraction, and this is what we have right here. So let me take that and actually, I'm going to duplicate that right away over here. And I'm just going to keep that as it is. And then I'm going to show you another way to solve for a and b without having to distribute. Okay, so what I'm going to do is I'm going to make a choice. I'm going to make a choice for what I want x to be. Remember, a and b are the things I'm trying to solve for, not x. So I don't know, pick your favorite number. 12 would work. 12 probably wouldn't be so helpful though. You could pick 17 if you like, or pi or e, but we want to maybe choose wisely. And let me show you what I mean by wisely. If x is 2, then this entire expression, x minus 2, turns to 0. And 0 is an easy number. That's why we're choosing wisely. Just zeros are easy numbers. We're just trying to make our numerical calculations a little easier. So if x is 2, then 3 times 2 is equal to a times 2 minus 2 plus b times 2 plus 4. I get 6 is equal to a times 0, which we know that a times 0 is just 0, so I don't even need to write it. 6b, and look at that, I got b equals 1. So I already knew b was equal to 1, but here was another way for me to get b equals 1. And then I still needed to solve for a equals in that method over here on the right. So in that case, I would just choose a different number for x. Ooh, sorry. I would just choose a different number for x and choose wisely. X equals 2 would have canceled the a completely. But I need to solve for a, so I should choose something that would cancel the b entirely, which would be -4. So if x is -4, then I get 3 times -4 equals a times -4 minus 2 plus b times -4 plus 4, and you know that b times 0 is 0, so it is now gone. And then I end up with -12 equals -6a, so I got a is equal to 2. Oh, look at that. So same solutions. So at the end of the day, it's the exact same thing. I still end up with that circled answer there at the bottom, which is my partial fraction decomposition. 2 ways to get the same answer. Like I said, the comparing coefficients method is definitely more of a guarantee. It works all the time, no matter how complicated this gets. But when they're nice and simple, when everything is linear, there's no x squareds anywhere, things are pretty, then this method, this let x equal method, just works nicely. So just a cool trick. So let's practice now with the calculus. So that's the idea of what partial fractions is. Now we just do the integral. So same idea, this particular problem is the integral of 3 over x squared minus 1, and I don't know that antiderivative right now off the top of my head. And maybe I could do try a U sub, that wouldn't work. I could try an integration by parts. You can give it a go, it wouldn't be helpful. You could try a trig sub. A trig sub would probably work here, but I'm just showing you another way. So I'm going to take my fraction, which is the integrand itself, so without the integral, and I am going to make sure that I first factor the denominator completely. So x minus 1 becomes x plus 1 times x minus 1. Sorry, I think I said that wrong. X squared minus 1 was a difference of 2 squares and factored as x plus 1 times x minus 1. And now I see that there are 2 factors on the bottom. So there should be 2 fractions, and I don't know what's going to be on top, so I'm going to call those a and b. And then I'm going to multiply both sides of that equation by the original denominator, which will always be your least common denominator. So whatever your original factored denominator was. And then distribute across, and sometimes lots of things will cancel, sometimes only some things will cancel. But always at least something will cancel. So on the left, I end up with just 3. That's nice and easy. On the right, I have an a times x minus 1 plus a b times x plus 1. And now this one kind of looks pretty simple to me. Everything is linear and pretty. So I'm going to make some choices for x. I think that will make my algebra a little smoother. If I let x equals 1, then this becomes 3 equals a times 1 minus 1 plus b times 1 plus 1. So I get 3 is equal to, it looks like 2b. Cool. All right, so then b is equal to 3/2. And I could probably also choose x equal -1. I'm just separating those two, so to make my life a little bit easier. And I'm going to do that same process. If that's the case, I would get 3 equals a times -1 minus 1 plus b times -1 minus 1. And I would simplify, combine my like terms, and I got a equals -3/2. Kind of more of a fluke. Certainly they're not always going to both be the same number, but there we have it. All right, so with that in mind, remember the original question was an integral. So let me go in and rewrite the original question. I was looking for the antiderivative or the integral of 3 over x squared minus 2. So now that can turn into a new integral of 2 different fractions, where I had a over x plus 1 and b over x minus 1. This is the a over x plus 1 and b over x minus 1, and I just filled in what I knew for a and b. And then the integral becomes a little bit easier. Oh, I've definitely run out of space. Let me give myself a little bit more. There we go. So now the integral becomes quite simple. Because -3/2 is just a constant, so it can stay. And then I have something that's linear on the bottom, which we know turns into the ln. And then the same thing for the other one, 3/2 ln of x minus 1 plus c. Ta-da! So the partial fractions makes integrals a little bit easier, but there's a caveat. It only is helpful if the denominator factors. If that didn't factor, then this whole method is completely useless. So just keep that in mind. So it certainly doesn't always work. Not everything factors nicely, but if it does, here's a really cool method to find another antiderivative. Okay, let's practice another one. Same problem, different numbers. First step is to make sure the denominator is completely factored. So in this case, it factors nicely. So I'll go ahead and do that. 1 over x plus 4 and an x minus 6. I had to stop and think about it, make sure we know how to factor. That's always going to be the first thing. And then it looks like I have 2 factors on the bottom. So I would have 2 possible fractions. We have that a and b are my unknowns. Multiply both sides of the equal sign by the original denominator. Distribute across and see what cancels. This would give me 1 equals a times x minus 6 plus b times x plus 4. Notice how both of the factors canceled on the left side. And then underneath the a, only the x plus 4 canceled. And underneath the b, only the x minus 6 canceled. And then again, similarly, this one looks kind of just like the one before. So I'm going to make that choice. If I were to let x equal 6, I would get 1 equals 10b. Pause to make sure that makes sense to you. So I got b is 1/10. Let's try the other one. We can skip some of the arithmetic. You can definitely skip some of the arithmetic. If x is -6 is probably not a good choice. Nothing would cancel. What about -4? -4 would make the b cancel, and this would turn into an a times -10. So I ended up, again, that's kind of a fluke. They certainly are not both always going to be the same number. I just gave you fluke problems. I don't know how to explain that really. It doesn't really happen all the time, but sometimes it does. Only when numbers are super easy. When everything factors super easily does that actually happen. Okay, so then this integral becomes the integral of a over x plus 4 plus b over x minus 6 dx. And then again, we know how to do that integral. So -1/10 ln of x plus 4 plus 1/10 ln of x minus 6 plus c. Ta-da! All right, that's the general idea for partial fractions using integrals. Let's do one that's a little trickier, okay? So I'm going to skip this part B here. It's very similar to the one we just did, so give it a go. Feel free to pause the video right now and see if you can try to do that one on your own, but definitely try to practice that one on your own at some point. But it's this one I want to do next. This one's a little bit different than the other one. So let's practice this one right here. So I've got the integral of 3 over x cubed minus 9x squared. Just like before, the first step is to make sure that the denominator is completely factored. And in this case, I have it factored. And then I'm going to break it up into multiple fractions. And here is the trick. This looks like there's only 2 factors on the bottom, but there's actually 3, right? This is technically an x times an x minus 9. So it's technically 3. And that x times x in the factored form is called a repeated linear factor. And the way you do partial fractions with a repeated linear factor, there's 3 factors, so it's going to be 3 fractions. The first one will have an x, but because it's repeated, the second fraction includes the repeat. So that would be x squared. And then the third fraction was not repeated, so it's the x minus 9. Then you're still going to do the ABC on top. Okay, so a little bit tricky. Let me give you a quick example up above. So definitely maybe make a little note to yourself. What if I had something like, I don't know, 4x plus 1 over, let's say, x plus 1 cubed times x minus 1 squared? Okay, this is completely factored, and there are 1, 2, 3, 4, 5 fractions on that denominator. The first one is going to be the x plus 1, and then it's repeated, so it shows up repeated. And in this case, because it was cubed, it shows up 3 times. And then you would have the x minus 1 the first time, and then the x minus 1 squared. And then you would have, in this case, A, B, C, D, and E, a little bit harder. Hopefully that helps you visualize how you set up the repeated linear factors for partial fraction decomposition. Okay, once you have it set up, then the process is exactly the same. Multiply both sides of that equal sign by the original denominator, because that will be the least common denominator, and then you distribute across and you see what cancels. All right, so we're going to do that. I'm going to get rid of this vocabulary on the left side of that equal sign. Everything canceled, and I got a 3. Over here, one of the x's canceled, but the other one did not. So I have an ax and an x minus 9. And then over here, both of the x's canceled. So I have a b times x minus 9. And then over here, the x minus 9 canceled. So I have a c times x squared. All right, and then I'm going to do the same process. I could distribute and then compare coefficients. If you want to do that first method, that would work. I'm going to try the other method here. It's actually a little bit harder, but it's not so bad. I'm going to choose, let's say x equals 0. That would give me 3 equals a times 0, which is gone, so 0, b times negative 9, so negative 9b, and then c times 0, so nothing. So that gives me b is equal to negative 1/3. Okay, and then I'm going to try another one. Let's try x equals 9. Okay, if x is equal to 9, this would be 3 is equal to 9 minus 9 is 0, so that's gone. 9 minus 9 is 0, so that's gone. And then 9 squared is 81, so I would have c times 81. So I got c is equal to 1/27. And then the tricky part about this method is I ran out of good choices. There's no other choice for x that will make something cancel, but I still only solved for 2 of the variables I need to solve for a. So I have to just try, even though it's not going to be a good choice. You just have to pick a number I haven't already used. So I'll just choose 1. If x is 1, this would become 3 equals a times 1 times 1 minus 9, which is a times 1 minus 9. And of course, 1 minus 9 is negative 8. So sorry. So that will turn into, there we go, negative 8a. Plus, and then b times 1 minus 9 is negative 8b, plus 1 squared times c is just c. And then you plug in what you already know. So I'm going to take the c and the b and plug those in over here. So I now have 3 is negative 8a, negative 8 times negative 1/3, and 1/27. And then use your calculator to simplify. Okay, really, truly use your calculator. That's exactly what I'm going to do. The 2 negatives cancel, then I have 8/3 plus 1/27. Make sure to click that math fraction button to simplify it as a fraction, and I got 73/27. And then I'm going to bring this to the other side of that equal sign by going 3 minus 73/27, use that math fraction button, and I got 8/27 is equal to negative 8a. So a was negative 1/27. Feel free to use your calculator, but you do need to know how to be able to do that with fractions, so make sure you know how to do that. It's okay to use your calculator, but make sure you are comfortable using your calculator with the fractions. Okay, now all that work, I haven't even done the calculus. So now I can do the calculus, right? So this becomes the integral of, I have a over x plus b over x squared plus c over x minus 9. Okay, I'm going to zoom in so that we can kind of finish solving that one a little bit maybe more carefully. Now, maybe you know the answer right now off the top of your head, and that's fine. I don't, so I'm going to simplify this a little bit. All I'm doing is I'm trying to break up which ones are going to turn into ln and which ones are not. So I know when it's linear on the bottom, that's going to turn into an ln, so I'm comfortable with those. But that x squared is not going to turn into an ln, so I rewrote it as the x to the -2, because then it's easier to do the antiderivative. So -1 over 27 ln of x minus 1/3. Then I can add 1 to the power, divide by the new power, plus 1 over 27 ln of x minus 9 plus c. Sorry for the confusion of the page number 24. Ta-da! All right. All right, let's do another one where they get a little trickier. They definitely do. I'm going to set up this next one. I won't be able to solve the whole thing, but I think it's a good one to set up. So 2 over x cubed times x plus 1. It looks like x is a repeated factor, but it shows up 3 times, so it's going to get the x squared, and the x cubed. And then the x plus 1 just gets the 1. Then you're going to do the a, b, c, and d. Okay, and then I'm going to multiply both sides by the original denominator, and then you are going to distribute across all sides of that equal sign, and some things are going to cancel. And I got 2 equals ax squared times x plus 1, b times x plus 1, c times x plus 1, and then d, sorry, there we go, d times x cubed. All right, and then this one is definitely a little bit harder to do the let x equals method. So this is the example that I wanted to do, where I'm going to show you to distribute and compare coefficients. So 2 is ax cubed plus a plus bx squared plus bx plus cx plus c plus dx cubed. And then I'm going to compare my coefficients. To compare the coefficients, what I'm going to do is I like to start off with the x cubed. What's in front of the x cubed? It looks like nothing is on the left side, and then a plus d is on the right side. And then I'm going to do my x squared. What's in front of the x squared? Well, there's nothing on the left side. And then there is a b. It looks like only b. Yeah, it looks like only b there. So I'm no, there wasn't a as well. I distributed wrong. Yeah. Oh, I'm so sorry. Look at that. That should have been an ax squared. I just distributed wrong. So then there was also a plus a. Okay, cool. All right. Then I'm going to look at the coefficients in front of the x. There's nothing on the left. On the right, there is a b plus c. Yeah, okay. And then if I'm going to look at my constants in this case, and the constants would be 2 on the left side. And then on the right, it looks like I have just a c. I just had to stare at it for a little bit. That was the only constant. Yeah, everything else had an x attached to it. Cool. All right, so then I'm going to do this. Like if c is 2, I can plug it into here. And you should be able to see then that b is -2. And then I can plug that into here, and I should be able to see that then a was, in this case, +2. And then I should be able to plug that into here, and I should be able to figure out that it looks like d was -2. Cool. And then integrate from there. Maybe actually I will finish this one. I think we might as well. This one's not as easy to do the calculus of, so let's do the calculus. That is going to turn into the integral of a over x plus b over x squared plus c over x cubed plus d over x plus 1. Okay, let's actually do that integral. So that's going to become, the linear is easy, so 2 ln of x. But then this x to the, sorry, negative 2 over x squared, in your head, you should be thinking of that as negative 2x to the negative 2. And then you would add 1 to the power and divide by the new power. Same thing for this other one. You can think of that in your head as 2x to the negative 3. And I would have to add 1 to the power, divide by the new power, and then of course when it's linear on the bottom we still have the ln, and then that would simplify to 2 ln of x plus 2 over x minus 1 over x squared minus 2 ln of x plus 1 plus c. Ta-da! Okay, really good. So I will skip the next one because it really is pretty much exactly the same. So try that one on your own as extra practice. That's a really good one. But this part C is the next example I want to do. Still an integral. This one's a little different. So we first had it when it factored nicely. Then we had it as a repeated linear factor. And now I'm going to show what happens when it doesn't factor nicely, but it still factors. So it still has to factor. And in this case, the denominator is factored. I have an x times x squared plus 4, but it's not super nice because x squared plus 4 doesn't factor any farther. So how do I do the partial fraction decomposition there? I still notice that there are 2 factors on the bottom. So I'm going to have 2 fractions, the x and the x squared plus 4. I'll still have an a on top of the x, but this has a new name. Because it did not factor any farther, this is called a irreducible quadratic. It's quadratic because of the x squared. It'd be cubic if it were an x cubed. Irreducible means this doesn't factor any farther in the real numbers. It does factor in the complex numbers, but we're not dealing with complex numbers right now. So irreducible quadratic gets a linear term on top. So like an mx plus b. I just chose the letters B and C instead of M, but it doesn't matter. They're just arbitrary numbers that we're going to try to solve for. So every time you have an irreducible quadratic, you're going to get a linear term on top. Okay, and then now you have the setup. Everything else is the same. The process is the same. You're going to multiply both sides by the original denominator, which is the least common denominator. You're going to distribute across. You're going to see what cancels. Let's go for it. I'm going to get an x plus 1 equals an a times x squared plus 4 plus a bx plus c times x. And then I'm going to go through and do just what we've done before. There's multiple ways that I can do this. You can choose the let x equals. I'll go ahead and do another compare coefficients. There's lots of benefits to both, so it's worthwhile to practice both. And then I'm going to look at my coefficients in front of, let's say, the x squared. First gives me, it looks like a 0 on the left and an a and a b on the right. If I look at the coefficients in front of the x, I have a 1 on the left and a c on the right. If I look at my constant coefficients, I have a 1 on the left and a 4a on the right. And so then I can solve. So a is equal to 1/4. C is equal to 1, so 0 is 1/4 plus b, so b is negative 1/4. All right, so then you go back to the integral, and now we do the calculus. This will become the integral of a over x plus bx plus c over x squared plus 4. Definitely a little trickier. I'm going to rewrite this. Now my c in this example was 1. I'm going to rewrite this over here on the right so I have more space. That's the integral of 1/4 times 1 over x plus, I'm going to break up the fraction, negative 1/4 x over x squared plus 4, and then plus 1 over x squared plus 4. All right, let me zoom in so you can see where I'm at. This is where I'm at so far. We can do it. This one in the middle, this is going to take some work. I'm not going to show you all the work. Pause and make sure you can do it on your own. But you would do a U sub there. All right, and then this one, I would do either a trig sub, like you just learned in the previous section, or maybe you just have that one memorized from Calc 1. Some of you guys might have memorized that formula from Calc 1. I don't know. Or trig sub. Trig sub is probably what I would choose. I don't happen to have it all memorized from Calc 1, but maybe you do. All right, but either way, then the answer is 1/4 ln of x. After I did a U sub, if you're willing to trust me, but make sure you pause and do it on your own to make sure you get the same answer. I got 1/8 ln of x squared plus 4. And then after I did the trig sub, I got 1/2 arc tangent of x over 2 plus c. Ta-da! All right, that's kind of all of the main pieces of partial fraction decomposition. You either have it factors nicely, or you have a repeated linear factor, or you have an irreducible quadratic. Those are the partial fraction decompositions. Once in a while, you're going to run into this trickier scenario where you can't yet use partial fractions, but you'll be able to soon. So this one is, it's still going to be one of those three methods, but before I do partial fractions, I have to first do long division. So when the degree on the top is bigger than or equal to the degree on the bottom, then you have to do long division. So if you're not super familiar with long division of polynomials, this might be a time that you choose to go find some YouTube videos about long division of polynomials. You're welcome to. I will just show you how to do the long division for this problem, and that might jog your memory. So here's how you do the long division. You have the bottom is on the outside of your division symbol, and then the top is on the inside of your division symbol. I should have given myself more space. And then you ask yourself, how many times does x squared go into x squared? Okay, this is maybe too easy. Once. If, for example, this was a 2, then how many times does x squared go into x squared? It would have been twice. In this case, it just happened to be 1, so it's 1. Now, it doesn't really matter, technically, it doesn't really matter where you put the 1. You could have put it over here or over there. I just like numbers on top of numbers, x's on top of x's, and x squared on top of x squared. That's just how I organize it. Technically, it doesn't matter. And then I do multiply. So I multiply that whole thing by 1, and I would have gotten an x squared minus 4, and then you subtract. Okay, so x squared minus x squared is 0. I'm not going to write it. 3x minus nothing is 3x. And then I have 1 minus a negative 4. 1 minus a negative 4 is a positive 5. And then you ask yourself, you repeat. You ask yourself again, how many times does the x squared go into 3x? Well, nothing, because one of them, they're not... x squared doesn't go into 3x at all because 3x is a smaller power or degree. So that means that 3x plus 5 is the remainder. So then this integral becomes the integral of the quotient, which was 1, plus the remainder over the divisor. Okay, so then this becomes the integral of 1 dx plus the integral of 3x plus 5 over x squared minus 4 dx. Now, the integral of 1 is easy. I'm going to come back to that later. Now, this is something I can do partial fractions for, because now the degree on top is smaller than or equal to the degree on bottom. So that's kind of the reason behind that. So I'll go ahead and do partial fraction there. 3x plus 5 over x minus 2 times x plus 2 becomes a over x minus 2 plus b over x plus 2. Multiply both sides of the fraction by x minus 2, or of the equal sign, sorry, by x minus 2 times x plus 2. Distribute across, see what cancels. 3x plus 5 equals a times x plus 2 plus b times x minus 2. I'll go ahead and do the other method. So we have one more time here. I'm going to run out of space. So I am going to give myself some space here. Just ignore the page number. I'm sorry. Oh yeah. Okay. So I'm going to let x equal 2. Then I would get 3 times 2 plus 5 equals a times 2 plus 2 plus b times 2 minus 2. And of course, the 2 minus 2 is 0. So then I get 6 plus 5. That was not a clear 5. I apologize for the sloppy handwriting. That's better. 6 plus 5 is 11. So I got 11/4 is A. Then I would maybe try to let x equal -2, and I would end up with something very similar. I would get -1 is equal to -4b. So b was 1/4. So then this integral became the integral of 1 dx. Don't forget, I got to come back to that integral still. So don't forget that's still there. And then I have the integral of a over x minus 2 plus b over x plus 2 dx. Now I can do that calculus. The antiderivative of 1 is x. And then when it's linear on the bottom, things are nice and smooth. Don't forget your plus c. Ta-da! It might be a good time to just have a throw out there a real good caution. What if you ended up with somewhere, and let's say an 11/4 over 2x plus 1? 11/4 is a constant multiple on the numerator, so it stays. And it is linear on the bottom, so it does become ln. But don't forget to divide by the constant multiple of 2 of that inside part. So just be careful with that. We haven't seen a whole lot of that in this video yet. All right, so that's partial fractions. That really is everything that you need to know for partial fractions. There's definitely some tricks and it requires some practice. So go back through, make sure you understand all these problems and the ones we skipped from this video. Try to go back in and see if you can do them on your own. Thank you.